Hi everyone. Today we are going to see automata theory. In this automata theory, the introductory concept we are going to see in this video. Some of the basic definitions and some introductions I want to give about automata theory. Here, this is the UG syllabus for engineers. In this first unit, these are the topics: deterministic finite automata, non-deterministic finite automata, and application to text search, finite automata with epsilon transitions. Okay, so here in this, the introduction to automata theory. What is automata? Actually, the automatic machine, like an ATM machine, is called as automata. Here in this ATM machine, we have given some input, right? What input we have given? We are inserting a card, ATM card in the machine, and automatically it can read the card, and then it moves to the next state. What it asks again, the next state is we have to enter the pin, right? So we have to enter the pin, and then it asks some amount. What amount you need to take, and or that one you have to enter. Okay, that is the state, next state. And then the final state, it gives the output, right? So these are the steps we are taken to doing the automatic machine, right? So here the automatic machine takes few steps to proceed the process, right? Here the states and the process are automatically doing by the machine, right? That machine is called as automatic machine. Okay, here the automatic machine, actually the automaton are abstract model of the machines. Okay, we are just doing a mathematical formulation. That formulation, the computer people defined as a computer program. That program is inbuilt in that automatic machine. After that, the machine can process the program. Okay, transit the program, that is called as transition. Okay, finally we get the output. Okay, here automata are abstract model of machines that perform computations on an input by moving through a series of states. The series of states. What are the states? We input the card, and then we input the pin, and then we enter the number, what amount we need. Finally, we get received the money. Okay, the input, the series of states. Every steps we called as states. Okay, at each state of the computation, a transition function determines the next configuration on the basis of a finite portion of the present state. As a result, once the computation reaches an accepting state, it accepts that input. Okay, in some of the cases, the card or pin are not matching. Na? It should not accept the state, right? It should not move to the next state. It says it rejects the card, right? And the pin number is wrong, it will tell, right? Sometimes it accepts when the pin number is correct, right? It accepts the input. The most general and powerful automata is the Turing machine. Okay, here this is the mathematical model of the or diagrammatic representation of the automata. In this automata, we have a input tape. This tape contains a input strings. Okay, one by one, the read and write head reads the symbol, and it is sent to the final control room. Here, in the final control room, it process at the transition function can transit. Okay, and then it accepts the string. Now it gives the output. Okay, only three parts. One is input tape, It contains the input strings and read and write head and a finite control room. Okay. So these are the three parts in the automaton. Okay. Next. There are four major families of automata. What are the families now? Finite state machine, push down automata, linear bounded automata, Turing machine. These are the four families. The automata above can be interpreted in a hierarchical form where the finite state machine is the simplest one and the Turing machine is most complex one. Okay, in that hierarchical form we arrange the family. Here the finite state machine, it's a simple one, and the automaton which the state set Q contains only a finite number of elements is called a finite state machine. Okay, only finite number of states. We input card and enter the pin, and then what's the process? We enter how much amount we have to get, and finally we received the amount. That's all. The states are finite. Okay. So ATM machine is a finite state machine only. Okay, va? ATM machine is a finite state machine because the finite set of states only. Okay. And just a few states or few steps that we taken to enter. Okay. So and the state transition function. The state transition function takes a current state and an input event and return the new set of output events and the next state. Therefore, it can be seen as a function which maps an ordered sequence of input events into a corresponding sequence or set of input events. In order to fully understand conceptually a finite state machine analogically to an elevator. Okay, in the elevator also a finite state machine. How can an elevator is a mechanism that does not remember all previous requests for service, but the current floor, the direction of motion, up or down. Elevator can move up and down, right? Move up and down, up or down, and the collection of not yet satisfied requests for service. Therefore, at any given moment in time, an elevator in operated would be defined by the following mathematical terms. First, states, finite set of states only in that to reflect the past history of the customer's request. Okay, next inputs, finite set of inputs only to have depending on the number of floors. Okay, first floor na, second floor, third floor. So which floor it have to reach. So elevator, lift. Okay, finite set of inputs only according to the number of floors. Okay, we can use the set I whose size is the number of floors in the building. Okay. So next one, outputs. Finite set of outputs only depending on the need of go up or down, which floor the customer wants to go, that about that the need the output should be, right? It is also finite. Okay. What what is the application of finite state machine? Traffic lights. Traffic light is also a finite state machine. Okay, it automatically transfer the lights. Okay, next video game, text parsing, CPU controllers, protocol analysis, natural language processing, speech recognition, the ATM machine too, a finite state machine. Okay, so here types of finite automata. Two types of finite automaton are there. One is deterministic finite state automaton. We call it as DFA. Non-deterministic finite automaton. We call it as NDFA. Okay. So here I want to introduce few definitions before going to the automaton briefly. Here, the symbol, a symbol is a character or a mark. That's it should be an alphabet or numbers. Okay. Alphabets. What is alphabet? A finite non-empty set of symbols is called alphabets. Finite non-empty set of symbols. Okay, it is denoted by sigma. See, for example, sigma equal to a comma b or 0 comma 1. Any finite number of numerals or alphabet entries. Okay, alphabet of machine language. Okay, so next definition, string or word. String, word, both are same. Okay, so hereafter I am telling string or word, both are the same thing only. Okay, the string or word is a finite sequence of symbols from the alphabet sigma. Okay, so alphabet sigma is a set of alphabet, right? From the set of alphabet, we produce some strings or words. A string formed from the alphabet sigma 0 comma 1. So, okay, using 0 comma 1, how can we write the strings? 0 1, 0 1 1 0, 0 0 1 1, 0 1 0. So, we arrange it. Okay, arrange it as a word or string, right? Using the symbols 0 and 1. Okay. Length of a string. What is length of a string? Here look at 0 1. 0 1 means two symbols in that. So the length of the 0 1 string is 2. Okay. Here 0 1 1 0. Okay. So 0 1 1 0 now here four four numerals are present. So we set the length of this string is 4. Okay, so similar. The length of the string is the number of symbols in a string. If W is a string, the length of the string is denoted as modulus of W. Okay, so here W, for example, we are taking the W as 0 0 1 1 0 0. Then what is the length of the string? Count it, 1 2 3 4 5 6. So 6 number of symbols in it. So the length of the string or word is 6. Okay. So next definition, empty string. The string with no symbols is usually denoted by epsilon. So that epsilon means empty string. Okay, epsilon means empty string. It contains no symbols. Okay, substring. Any string of consecutive character from a sequence, the W is called as substring of W. Consecutive character before entry or final entry, that is called as substring. Okay, yes, some substrings as usual, like the subset. From a set, we say some subsets, no? We find some subsets, no? Similar. Okay. So the reverse of a string. The reverse of a string is obtained by writing a symbol in reverse order. Okay. Here A1, A2, etc. AN in reverse order from AN to A1. Okay. That is reverse of a string. W power R. Prefix and suffix of a string. Prefix is a string of any number of leading symbols and suffix is any number of trailing symbol. That means from the reverse order we make it, that is a suffix. From the first to last we make it the strings, that is called a prefix. Okay. Here W equal to AB, BAB is a word or string given. The prefix of this word is always the empty string also contained in the word. Okay. So epsilon is an empty string. From first we are starting A. From first AB. From first ABB. From first ABBA. From first ABBAB. Okay. From last suffix epsilon. Last string is B, and from last AB, from last BAB, from last BBAB, from last ABBAB. Okay, so this is prefix and suffix. Okay, leading symbols. Concatenation. Concatenation means it's just a, it's looking like a product. Okay, it's like a product. String of words two words we can appending in the symbol of strings. Okay. Obtained by appending the symbol of string U to the right end of string W. Okay. This is concatenation, like a product. Okay. Next, clean star. Clean star or clean closure of a string that we define using star. Okay. Epsilon, the sigma is an alphabet, then sigma star is obtained concatenating 0 or more symbol from sigma. Sigma equal to 0, comma 1 and sigma power 0, that means a empty string. Okay, this word length is 0. Okay, no strings are there, no symbols are there, empty string. Sigma power 1 and length 1 symbols. Sigma power 2, length 2 strings, strings with length 2. Sigma star means this everything union concluded, included. Okay. So sigma star na epsilon empty string including empty string to all length strings. Okay. Strings with all length. Next, positive closure. Positive closure na you just subtract the empty string from the clean closure. Clean closure means all length of symbols, right? In that all length of symbols, you just remove the empty string means it is called as positive closure. It is defined as sigma plus, okay, without epsilon. This all length of strings without epsilon. Okay, language. Language can be defined as a set of strings obtained from sigma star where sigma denotes alphabets of the language. Language L contained in clean closure itself. Okay. So for example, sigma equal to A comma B. Okay. Here clean closure na epsilon empty string A, B, AB, etc. all length of strings using A comma A, B, right? The language of strings consisting of equal number of A's and B's can be L1 equal to AB, AABB, ABAB, BABA, etc. etc. The language of strings consisting of n number of A's followed by n number of B's, m number of B's, where m greater than or equal to n. So, n number of A's and m number of B's, m greater than n. Okay. So, L2 ABB, AABBB. So, A's the number of A's are n. So, number of B's are more than number of A's. Okay. In every string, number of B's are more than number of A's. Okay. So, next. Complement of a language. Complement of a language L is denoted by L complement. So L complement language na already L complement means clean star minus language. Okay. So the reverse of a language. Actually language you can take it in the reverse order the strings are writing na that is called as reverse of a language. Concatenation already you have completed of two languages means just a product like that L1 L2. Okay. Clean star or clean closure of language means all languages included the epsilon language, empty language. Okay. The positive closure of a language means L plus L1 without the empty language L0, without the L0. Okay. So thank you. See you again in the next video. In the next video, I will explain what is non-deterministic finite state automata. Okay. See you. Bye. Bye. See you.